And now that we've taken attendance and done some FERPA-protected stuff, here is our Blackboard homepage. Like I said, I'm Dr. Spurko, and one of the things that you may want out of me is you may want to ask me questions once in a while. I'm perfectly happy to answer questions by email. I have turned on the Ask Your Teacher functionality in WebAssign so that when you're looking at a particular homework question, there'll be a button there up to the right that says Ask Your Teacher, and you can type your question to me, and I'll already see the homework question that you're working on so that you won't have to repeat all that stuff. So that makes your job of asking questions a little bit more efficient. It reduces barriers to your getting help. But you also may want to come and have face-to-face visits with me. And in that case, I am in the NRC building. That's all the way down past the parking garage, past the new biology building, which is still a construction site, but won't be next semester. Across the street, it's the second building in from the bay. And I am in room 1111, which is inside the 1100 suite. So the first thing you got to do is go on the first floor and find room 1100 and go in there, and then you can look for 1111. And you need to know when to find me. So I've posted my kind of university calendar. It's a Google Calendar here. And you can see I have office hours scheduled currently for Tuesday and Thursday at 1 p.m. and also Wednesdays at 11 in the morning. Now, if none of those times work for you, notice there's a lot of blank space in there. Now, that blank space is when I figure out what I'm going to say to you, and when I grade labs and prepare homeworks and write exams and grade exams and all that. But it's also time when I could set those activities aside and actually talk to one of you. So if you need to talk to me and the office hours don't work, email me, suggest a time, find a blank time, say, hey, would you by chance be available on Wednesday at noon? And I could say, yeah, absolutely. I can put off my lunch for another half an hour or so. If you suggest Friday at 5 p.m., I'll say no. Anything pretty much after 5 p.m. is a little unlikely, but definitely not Friday. If you suggest 7 in the morning, I'll say no. But as long as you're suggesting, I'd like not before 9, but if you really need to talk to me at 8, we could probably do that. So that's how you can get a hold of me. And then we'll set up a time, and it'll show up on my calendar, probably something like this thing next week, where next Friday it says I'm meeting a student. So that's what I put in my calendar there if I've already dedicated that time to somebody. Now, you also probably want to know an idea of what we're doing. I've set up a calendar of each lecture day in our class. So today I'm giving the intro. We're going to talk about electric charges and electric force. We're basically going to be talking about stuff that I think is from chapter 15, or maybe it's called lesson 15 of our book. There was some kind of a new age shift in our textbook of not calling things chapters in the 11th edition. But if I've gotten these textbook things wrong, somebody let me know and I'll fix them, and I'll go back and look at the book again. But we're going to spend the next month basically talking about electrostatics. That's the first bit of stuff, and then DC circuits. And then we'll have an exam 1. I'm pretty comfortable saying that exam 1 is going to be at the end of week 5. So you can put that in as our exam time for the first exam. As far as homeworks are all going to be on WebAssign. I think WebAssign is the least bad of the systems of homework. I've talked to people about one of the other systems called, it's UT something. It's from the University of Texas. And the students who had that said no. Yeah. I've talked to people who've used Mastering Physics, which is basically the same as WebAssign. I don't think it's significantly different from your experience or from your perspective. So we are using WebAssign. So that means that you need WebAssign Access this semester. That's the only absolutely required textbook is WebAssign Access. It does come with an ebook version of our textbook. WebAssign has several different methods for you to pay for this. One is that you can buy the book from the bookstore. Maybe you bought it in Physics 1, and that comes with a little card with an access code that gives you life of edition access. So if you took Physics 1401 in the last probably 3 semesters and used that access code from the book, then WebAssign should automatically continue to give you access. Another method is that you could buy it on their website, so they're perfectly happy to accept your money. I think they have single semester, single class. They have life of edition access, which is for Physics 1 and Physics 2. Now, you're already in Physics 2, so hopefully you wouldn't need another semester after this, but you never know. And they also have a single semester all classes option this year. I think it's called Cengage Unlimited. And that is if you're in a math class and the physics class and we both use WebAssign, you can kind of lump them together and pay one fee instead of 2 separate fees. I don't know how much it actually saves you, if anything. So let me click over here to WebAssign, control click so it goes in a new tab. What? I've been out of Blackboard so long that it forgot that I'm in Blackboard. Okay. Yeah, there we go. But the campus single sign-on site believed me. Okay. So I'm in the process of getting on WebAssign here, blah, blah, blah. So here's our class. You see, you don't get this view, you get a slightly different view that should look more like this. Currently, there are no assignments because I haven't posted homework 1 yet. I'll get that done in the next day or so. But I did turn on this thing called the personal study plan. That's kind of extra homework questions that you can work on. As we get close to exams, there's always a bunch of people that ask me, is there any extra stuff that we can work on at practice? And that's what I would point toward. And we'll be down here starting to work in chapter 15. So I have flagged the first 3 sections of chapter 15, or the first 3 sections that they provide, and said, hey, these are actually things that we're going to be covering. So if you're hurting for stuff to do in the next couple of days before I post homework 1, there you have something you can work on. Like I said, I am archiving these classes, and I figured if I'm saving it in YouTube, then I might as well let you look at it in YouTube. So there is a YouTube playlist for us. And currently that YouTube playlist is empty because I haven't recorded anything. I didn't make a welcome message or anything like that. I didn't have a 5-second thing telling you to subscribe to my channel. It's purely our class. That's all I'm going to put in here. But this is where the class recordings are going to go. We might have an SI this semester. I'm not sure what the SI situation is right now. So if I learn more about that, I will put that there. As far as lab goes, this is a laboratory course. That's part of the reason why your majors tell you or suggest to you to take physics. All of the lab stuff is on this website that is also going to be pointed to by your lab instructor. And then the actual lab reports will get submitted over here in the lecture page so that we can organize all your grades and you can always see the most current grade for how you're doing in the course. I'll leave it for your lab instructor to remind you how the physics labs run here, but it really is basically the same as it was in Physics 1. The actual textbook is this College Physics by Surway and Vuel. It's a reasonable book. I've looked at all of the introductory physics textbooks, and they're all basically the same. So if you think it's a lousy book, nobody's made one better. And I do recommend that you read the book. I think that a multi-pronged approach in trying to learn and understand physics is your best bet. So listening to me and watching what I do is one prong of that process. Another prong is working on homework. Another prong is reading the book. Another might be looking at other people's tutorial material. So there's a website called Physics Classroom, which covers a lot of the stuff that we're going to cover at the algebra-based level. And that's a possible source. A lot of people know about Khan Academy. Khan Academy tends to be a calculus-based physics curriculum, but if you find that Khan Academy is going over a question that's very similar to what we've gone over, they're probably using the same techniques we do, because you don't have to use calculus for everything in every physics analysis. And of course, going to CASA, to the tutoring center, I think is a good idea, especially once you've started working on your homework and you've gotten to a point where you're stuck. Bring in work that you've done so far so that you can show the tutor where you're at and they can address the thing that's making you stuck. And hopefully, once you get unstuck, then you can pick up the ball and run from there. So I suppose we do have a syllabus, even though most of the important information from the syllabus I've put into Blackboard directly. We do have a syllabus, so I should probably click over to it and point out the things that are not on Blackboard. The thing that I want to point out is this page of the syllabus, where I describe how the grades are going to be produced. So basically, our course has laboratory and homework, which are 25 and 15%, total 40% of your grade. I think of those as being like effort grades, because you basically get credit for the homework if you work on it. You get most of the credit for the labs if you work on it. And then we have these 3 exams, exam 1, exam 2, and final exam. And I think of those as assessment grades. So our course is basically 40% effort, 60% assessment. And in order to help you get a better grade, I have 2 things in mind. One is I will give you a few bonus points on your homework for working on it early. So once I get it posted, there'll be a due date. Anything you do more than 3 days before the due date, instead of getting 1 point per question, you'll get 1.25 points per question. In other words, 25% bonus on anything you do early. So that's one thing. And the other thing is that it is fairly common for people to have a bad day and not do well on an exam. But you do pay for your courses, take your courses and get graded a semester at a time, not a month at a time. So I figure if you can do well on the final exam and demonstrate your knowledge of the course material, that you should get credit for that as well. So to accomplish that, if your final exam grade is more than either or both exams, I will replace your exam grade with the newer, better final grade. And that has a tendency to help out a good, well, usually roughly half the class gets a little bit of a benefit out of that. So those are the opportunities I have for extra help in your grade this semester. It's one or both. The way I phrased it, and I don't see too much of a reason to change, is it's going to be both if necessary. Now, with that being said, I'm not going to do it for an unexcused absence for an exam. So don't think that you can just skip out on an exam and automatically get the final exam grade. So you have to show up and try. There's a topics list here as well, though I would say that if I have to rearrange exactly where the topics are going to go, I'm not going to update the syllabus. I'm going to update Blackboard. So the Blackboard version of this table is going to be the most up-to-date at any given time. And then all of the policies and stuff are in here. I have gotten a few notices already this semester from Disability Services. If you're using the testing center, go make arrangements with them. They email me, I send them a test, I come pick it up, I say hello to them after you take your test, and it works really well. So don't be afraid to use the services provided by that office. And please note that if you do have to drop the course, you have to drop the course. You can't just stop showing up. That doesn't work. All right, so does anybody have any questions that what I would call, that fall under a category I would call administravia? Then, one thing I didn't point out is there's going to be a web folder here, which is just an old-fashioned web server. It's literally a folder full of files. This is where I'm going to put the readable PDF version of the notes. So that'll appear there below the syllabus. But you can see my notes from previous years there. So if you want to know roughly what we're going to do in any given day, you can look at the notes from the summer or from last fall and see what we did after that topic previously. The order of topics doesn't change all that much. And the way I teach each topic doesn't change too much from year to year. So that gives you an idea of how things are going to happen. Now, previously, as in last year, I had done my notes on paper and projected them on the screen using these wonderful document cameras. But I have modernized myself. I think it was at spring break, I got an electronic pen and a tablet. And then at the end of the semester, my tablet broke and I got a new tablet and used a different tablet over the summer. And the new one still works, but it only works in my laptop. I can't plug it into the lecture computer. So I have to bring my laptop every day. But I still get to use Microsoft OneNote. I like this better than using paper. It gives me the chance to use color and things like that. So I've started our class OneNote file. I'm going to, after today, convert it to PDF, post it on the course web folder. And then one of the things that you can do is pull up that document and click through to OneDrive, which will give you a live read-only version of the notes. So you could potentially have my notes on the screen in front of you while you're taking notes on paper, so that when I flip screens and scroll things off the top, you would still get to see them. But just because you have all of these resources, you have my notes that I'm writing on the screen, you have a recording of my voice, at least I assume it's still recording my voice. Is it still recording? Yeah, it's still recording my voice. That doesn't mean that you shouldn't be here. You absolutely should be here. I think it's really important. And it doesn't mean you shouldn't take notes. You should take notes. It just means that you have more resources than if you just had me talking and you taking notes. So these extra resources don't replace the in-class experience. At least if you're here, I can look at you and I can see how boring I am. Whereas if half the class stops showing up, then I have no idea how I'm doing. And then I can't readjust myself and make things better. So I started this by just putting more of the syllabus type stuff in here. I literally copied and pasted it. But what I'm going to do here is say Lec 1, charges and electric forces. And these tabs at the top of my page, I think, are sections in the OneNote version. And that will serve to distinguish each lecture from the others so that at least when you go back and try to find the notes later, you can find what we were doing. So, introduction to electrostatics. And one of the quirks of my, my hand-eye coordination is that I type faster than I write. I also type much more neatly than I write. And both of those are good for you. So sometimes I'm just going to literally type things in front of you. It'll go faster than it used to when I used to write it out on paper. So the first thing I'd like to address is, why did we study this stuff in the first place? Our course is a study of electricity and magnetism. It's the very first introductory level. For somebody like me who gets a PhD in physics, I ended up taking 6 separate courses on electricity and magnetism, starting with this one. So it's not like you're going to learn everything about electricity and magnetism, but in order to understand what's going on at the higher and higher mathematical levels, you kind of have to have some intuition built up. And that's what this course is about, is getting a little bit of intuition about how electricity behaves, and then figuring out how electricity and magnetism work together to create light and radio waves and things that we can see and things that we need to deal with. Now, one of the things about electricity and magnetism, ever since we figured it out in the late 1800s, our society has become more and more electric. We use electricity for energy. So we power motors, which lift things, that push things, and move stuff around for us. So that's one of our end goals of using electricity. What else do we use electricity for in our lives? Any ideas? Heat is a absolute important form. Well, it's an absolutely important use of electricity, and heat is a form of energy. I'm teaching another course this semester called thermodynamics, and in that course, we're going to talk about heat and how it's related to energy directly. So that's absolutely true. I'm going to put that in that first bullet point. So heat, light, movement are all different things we do with energy. Cooking. How about this one? We use electricity for information. So we use electricity to communicate information, to get information from one place to another. We use electricity and magnetism for storage of information. My laptop is of the old style. It still has a spinning hard disk inside it, and that spinning hard disk has lots of little tiny magnets. And those magnets are used to store all the information that the laptop knows about in order to be able to accept my input, display its output. And the laptop runs on batteries. In fact, probably the biggest use of my laptop battery, and the reason I have to plug it in, is because of the processing of information. It takes effort to think. And for the computer, that's not much different than it is for you. It takes energy for the computer to think. It takes effort for us to think. After you've worked on physics homework for a couple of hours, you're tired. So these are different things that we do with electricity. And you know we need electricity. You know it's important. Every time you go to an airport, you see people lined up along the walls trying to use the outlets to charge their phones. Our phones run on electrical energy, and when it runs low, we freak out and we say, I need to have some energy. So, so that's one reason we like to study electricity and magnetism. Another reason is that electricity and magnetism are behind light and radio waves. And it's good to understand more about the world around us. So if we understand a little bit more about light, infrared, radio waves, X-rays and stuff, then we can better understand the way our end jobs actually interact with the world. Electricity and magnetism are actually the basis of chemistry. Now, you can't just use the idea of forces and acceleration that we did in Physics 1 as your mechanics, along with electricity and magnetism, to create chemistry. You need an alternative mechanics called quantum mechanics. And if you want to learn about quantum mechanics, I would encourage you to look at some of the cartoony, I call them, YouTube series of physics where you can learn more about quantum mechanics. We're not going to cover quantum mechanics. I don't think most of you are required to take any quantum mechanics courses, but it's part of what goes into chemistry. I kind of made up that phrase. That's not going to look the same next time I teach this course. I'm going to come up with a better way of writing that last bullet. But the basic idea is that we use electricity and magnetism and light and radio waves to learn about the world around us, to learn about ourselves, to learn about patients and subjects and equipment and stuff. And we use electricity and magnetism to control the equipment and sometimes to directly affect the things that we're trying to deal with. How many of you are in some kind of biomedical field? Okay, that's too many. How many are not in a biomedical field? So what are you in?
Physiology.
That's a medical field. I know it's not biomedical per se, but it is a science of dealing with people.
Environmental science.
Environmental science, very important. Not dealing with people, absolutely. What else?
Geology.
Geology, also fairly important and not dealing with people. So whether you're dealing with a biomedical science, including kinesiology, or another science, electricity and magnetism are used as part of the equipment. And just having a basic idea of how electricity works can help you figure out why your equipment is broken, and it can make the difference between getting your work done that day and having to call a consultant and pay him thousands of dollars to come fix it. And it's always better to fix something on the spot without breaking it worse than it is to pay a lot every time there's a quirk. And just in case you think that the stuff that we do here has absolutely no application to what you're dealing with, my fallback is that what we are doing is practice in mathematics, which is fairly important in most scientific fields, and it's practice in the process of learning. Because in this class, we're going to look at evidence and observations and then use those to back up theories about how it works. And that's a process of learning about new things. And part of being at a university is learning about lots of different new things, training your brain to learn, not just learning the things you're studying, but learning how to learn things. And that's something that maybe we don't know, we as a scientific community don't know quite as much about as we could, but I think it's not going to be all that long before there are, I don't know, non-money-making ways of training your brain. As far as I know, currently, all the things that claim to train your brain are still people who are trying to make money. They're not necessarily true brain trainers. But feel free to prove me wrong on that. All right, so electrostatics. I need to do something on this computer. File, options. I need to have a bigger default font size. And personally, I don't like that font. You know what font I like? Times New Roman. And the fact that I like Times New Roman makes me a dinosaur, unfortunately. So, first of all, let's get started with thinking about charges. All matter, all material, all stuff is made out of atoms. And, whoa, I thought I changed my font size. It's refusing to change my actual font. It's going back to Calibri. I'll figure this out before Wednesday. Oh, it was lying. Okay, so atoms are the tiniest bits of material that is still basically the same stuff. Now, hopefully all of you have had some introductory, even middle school level chemistry that you've seen these things before. Wow, if I click away from the box, so in an atom, the protons and the neutrons are gathered in nucleus. Whereas the electrons orbit around the nucleus in a cloud. So that's our basic view of chemistry. There's a lot to that, and people make entire careers about studying how electrons move around in their cloud, how they interact with each other. Now, these particles that make up atoms are kind of, they're very well defined. Each proton always has the same positive charge And each electron always has the same negative charge. Now, charge is a property. It is it's a kind of a numerical quantification. It's a measurement of how electric something is. So each proton always carries the same amount of positive electricity. Each electron always carries the exact same amount of negative electricity. Now I can write these things in equations, and let's see if I can get the pen working here. The Q of a proton is equal to plus E, and the Q of an electron is equal to minus E, and E is 1.6 times 10 to the minus 19th charge units. The charge unit is called the coulomb, named after a guy. And as it turns out, when we were doing our first experiments with electricity and decided how big a coulomb was supposed to be, they picked an amount of charge that's kind of pretty big. And that means that when you measure a single electron or proton in those units, the quantity turns out to be really small, a tiny fraction of a coulomb. That 10 to the minus 19th might be the smallest number you've ever seen that is still greater than 0, that's still positive. This quantity is called the elementary charge. Oops. So any given molecule, any given material is going to have a certain number of protons and a certain number of electrons. And one of the interesting things about charges is that if you accumulate all the positive charge and all the negative charge, they can partially cancel by the process of addition, just like positive numbers and negative numbers cancel each other out. And that's why we chose to call some of them positive and some of them negative, because we could say that we have a certain amount of proton charge and then a certain amount of electron charge, and then say, oh, well, the total effective charge is the proton charge minus the electron charge. But it is nicer to be able to say, well, there's this thing called charge, and the amount of proton charge is positive and the amount of electron charge is negative. So that's what we did. Now, as it turns out, unless you're going to do some particle physics and really blast the heck out of stuff, you cannot do anything with protons and electrons other than move them around. And if you combine these ideas that you can't create or destroy protons and electrons, and they're always the same, that means that the total amount of proton charge and the total amount of electron charge are always the same. Sure, you can take some electrons and move them from one place to another. You could take some protons and move them from one place to another. But you can't create or destroy them. You can only move them around. And all of the real electricity that we deal with involves moving charges around. Generally, the protons, the positive charges, stay in place. They're attached to the nuclei, which kind of defines the material. So there are a few exceptions, and I don't want to set a hard and fast rule that's a lie on the very first day of class. So I'll give the exceptions first. There are things called nuclear reactions, which are possible. They generally don't happen in everyday life. They happen in special places that we put off in the middle of nowhere so they don't hurt anybody. You could have particle physics experiments that could have beams of protons moving around. You could have chemical reactions. And chemical reactions involve taking atoms that are attached to each other and making them not attached so they can be attached to other atoms instead. Really, chemical reactions are all about the electrons. They're not about the protons. But basically, they involve moving nuclei around so that nuclei can be attached to other nuclei. And you can also have material flow, as in water flowing or air blowing or something like that. And in that case, you could have some protons moving around. So these last two things, scroll down. These last two things happen inside a battery. You know, the wonderful lithium-ion batteries that power our cell phones and flashlights and laptops. There are some chemical reactions that happen at the two ends of a battery, and there's some material flow inside of a battery. Lithium ions actually move around inside a liquid. Now, those three things are more rare. They're less common than other ways of having electricity move around. So unless something weird is happening, then it's just the electrons that are flowing. Thank you. So that means that we basically have some stuff, and there's some negative electrons in the stuff, and the negative electrons move around. And that's a description of what happens in a wire, in a cable, when electricity flows. The wire stays put, the metal stays in place, and the electrons move around. So that's the flow of electricity in wires. Now, there's a side effect of all of this that I've described. Electrons are the negative charges, but electrons are the mobile things that move around. And that means that when we talk about the flow of electricity, there's two opposite directions that are involved. There's the direction of the electricity flow, and there's the direction of the electron movement. And they're opposite to each other. And usually that doesn't matter. And we kind of ignore the electrons and just think about which way is the charge flowing, which way is the electricity flowing. That's called the conventional current. Very rarely, but every once in a while, it's important to think about the direction of the velocity of the electrons. And we just have to remember in those cases that it's the opposite way. But usually, in everything in our course, except for, I think, Lab 6, where we look at the motion of an electron, we don't care about which way the actual electron is moving. We care about the direction of the charge motion. Now, from physics 1, the most basic thing we described as an interaction between objects is a force. We talked about force, we talked about impulse and how it relates to momentum, and we talked about work and how it relates to energy. But the basic idea is a force. And for electricity, that force is called the Coulomb force, after the same guy that we used to measure to create the units of charge. Now in physics, we like to study the easy stuff first. Even though maybe the easy stuff isn't as applicable to a real world application as what we ultimately want to get to, we want to study the easy stuff first. And the easiest case to study is two small charges that are well separated from each other. And in this universe that we're thinking about, there are no other charges. So as an example, we could have two opposite charges. So over here, I'm going to draw a plus charge. And the way I represent a small positive charge is I draw a circle to represent the actual stuff, and I put a plus sign on it to say that it's positive. And then I can represent the negative charge in the opposite way by drawing a minus sign, putting a little circle on it to represent the idea that it's negative. And I'm going to say here, I'm going to call this one Q1 is plus 8 nanocoulombs, and this is Q2 is minus 5 nanocoulombs. Now on the previous page, I wrote down this thing, E equals 1.6 times 10 to the minus 19th coulombs. So question for you. Let's say that Q2 was just made out of electrons. Electrons are negative, Q2 is negative. So you could maybe build Q2 out of electrons. How many are there? So does anybody remember how big a nano is? Yeah, 10 to the minus 9. So then, is the elementary charge bigger or smaller than that? A little bit smaller or a lot smaller? That's a lot smaller. So this Q2, if you build it out of electrons, would be built out of like 10 to the 10th electrons. It'd actually be built out of, it's about a sixth of 10, so it's about a third of 5. So it'd be built out of like 30 billion electrons. And then the Q1 could possibly be built out of protons, and it'd be built out of, I don't know, 50 billion protons or something like that. So we're talking about a lot of charges here. But from our perspective as scientists in the late 1800s, these are really tiny charges. We don't know about electrons yet. And the most basic rule of the force between charges is that opposite charges attract. So that means that these two things exert force on each other. And this one feels a force pulling in that direction. And this one feels a force pulling in that direction. So we could call it F sub E. E for electric. So you could call it the electric force or the Coulomb force. Usually if you're talking about just the static electric force, we call it the Coulomb force. So that is our setup. And what we expect out of this is we expect that this force should depend on how electric these things are, should depend on the Q values. And we also expect it should depend on distance somehow. Because when things happen really far away, we don't notice them. We don't feel all kinds of weird forces acting on us from all kinds of weird different things on the other side of the universe. So whatever rule we get for the electric force has to be one that involves a smaller amount of force when the charges are small, and it also has to be a small amount of force when the distance grows. So here's the rule. F electric is equal to K Q1 Q2 over R squared. We need some definitions here. K is 9 times 10 to the 9th Newton meter squared per Coulomb squared. Now, like in physics 1, in physics 2, there are lots of formulas and there's a few quantities. And both this formula and that quantity are going to be on your equation sheet that you get to use during exams. So it's not something where you have to memorize lots of different numerical values. But if I'm going to do an example with it, I need to write them down here. And then the absolute value bars are there to stress the idea that I'm talking about the magnitude of these two Q values. Sometimes we run this formula without the absolute value bars, and if you're careful about your directions, the result can come out positive or negative, and you can know what that means. I like to run the formula with all magnitudes and get a strength of the force, and then apply that strength to the direction that I know the force is in. I know that the force is supposed to be attractive if the particles are opposite charge. And the inverse of that is also true. Similar charges are supposed to repel each other. Now this R is the center to center distance between these charges. This is actually a lot more loquacious than it needs to be. I don't need that many words because, after all, these are small charges. The center and the edge are basically in the same spot. So really, it's just the distance between the two charges. So I suppose in the example, I need to give a distance, let's say 0.25 meters. So add that as a dimension on the diagram. And now I can actually calculate how much force there is. So this would be F electric is equal to 9 times 10 to the 9th Newton meter squared per Coulomb squared. 8 times 10 to the minus ninth coulombs. 5 times 10 to the minus ninth coulombs. Over 0.25 meters quantity squared. And if you put all those together, I believe the result comes out to 5.76 times 10 to the minus 6 newtons. I believe the numerical part because I worked at it and typed it in my calculator before. And I believe the units part because I can see the units happen. We have newtons as part of the constant. That's actually what that constant does, is it gives us the newtons. It also cancels out the 2 Coulomb factors that are there. And its meters squared cancels out the meters squared from the bottom of the fraction. So the units all work out. And we might write this as 5.76 micronewtons. So that's the most basic thing that we can do with electrostatics. Now, we don't, in everyday life, tend to deal with individual charges very much. So it's more likely that we might deal with a charged object. And in that case, here's a metal ball. Now, metal is a type of material. It's exactly what you're thinking of, like steel or something like that. And there's one property of metals, that it's a conductor. That means the electrons are free to roam around where they want. Now, if you just have a regular piece of metal, the electrons end up just spreading out all over the place because the nuclei, the actual metal itself, is also spread out all over the place. And the electrons, sure, they don't like each other. They're like charges that repel, but there's so many positive charges that the electrons are perfectly happy. So you end up with this smooth distribution of positive charges along with a smooth distribution of negative charges, and everybody's happy, and they cancel each other out. So I should write what I just said. What I just described are balance charges. They spread out throughout the metal. Any extra charges, on the other hand, will repel and go to the edges. So if you have a metal ball and somehow you give it extra electrons, maybe you zap it with lightning or something like that, then those extra electrons, at least in a two-dimensional diagram, are all going to head for the edges. Going to spread out throughout the entire thing. And the middle of the object, that is the actual inside of the metal, is neutral. All of the extra charge is at the very edge. So there's a weird situation that is more likely to come about in physics class than it is in real life. But what if I have two charged metal spheres and bring them into contact with each other? So then we're going to have I'm going to draw the contact as a wire. So I've drawn this barbell diagram where we used to have a +8 nanocoulomb charge and a -5 nanocoulomb charge, and I've brought them into contact. So these -5 nanocoulombs here are going to try to get away from each other. And it used to be that they were stuck on the right-hand sphere. But now with that extra wire, they're allowed to spread around to the other side. The same thing happens with the 8 nanocoulombs. They're allowed to spread out all over the place. So both charges end up spreading out to both sides of the system. And if the two objects are actually symmetric, then the charges end up being symmetric as well. Now, if you had one that was tiny and one that was gigantic, then the amount of charge each gets will not be symmetric. But if they are symmetric, then this is what happens. So Q total is +8 minus 5 is +3 nanocoulombs. So new Q1 is +1.5 nanocoulombs, and the new Q2 is +1.5 nanocoulombs. So now the force that exists between these two objects is going to be different than it was before. One, the strength is going to change a little. What about the direction of the force? Now they're the same type of charge. They're both positive. So now they're going to be repelled from each other. Yeah. And this is one of the things that helps lightning to blow things up. When lightning strikes, things scatter all over the place. One of the reasons for that is a large release of energy, a large amount of heat, like a bomb or a laser blast. But another thing is lightning carries charge, and when the lightning comes in, all those things get the same amount of charge, whether it's positive lightning or negative lightning, and then all of a sudden the object doesn't want to be near itself anymore, and it blows up. This can happen with a Van de Graaff generator. You can kind of see it if you do an experiment involving a plastic comb and lots of little bits of paper. Sometimes if you run a comb through your hair and bring it near little bits of paper, you can see the little bits of paper attracted to the comb, but every once in a while, one of them will just decide to jump away. And if you see one jump away, it's because it came into contact and gathered that charge, and now all of a sudden it's not the opposite charge anymore, now it's the same charge. And now, instead of being attracted, it runs away. All right, well, it is now the end of our class, so I should let you go because we all have other classes to go to. And I'll see you guys in here on Wednesday.